Today I am using two devices so that you will see me writing on the board. The board is here. So I will look down and you will see my head. Okay. Are we all here? I read the number 16 minus 2 because I am 2 times in the call. So 14, is it right? 14? 15 now. Okay, let's wait until 6:05. Okay, I think we are all here. Good. Are you here?
Yes.
Yes.
Good. Very good. Now I want to start by having a very small recap where I want to mention the fact that we have considered the two general subjects. The first subject is confidentiality. And we used symmetric encryption. Then we considered also integrity. And we saw that the most important tool for data integrity is consisting of hashing functions. We know that hashing functions, they can have some issues with the collisions. In addition, we want that the hashing functions we are using, they should be cryptographical. I guess you remember the meaning of cryptographic quality for a hashing function. And the two subjects, confidentiality and integrity, they are very important, and I think they are among the most important concepts in information security today. Now, first, I want to ask whether there are any questions about these subjects we covered in the first lessons. This is the fourth. So the first three were covering symmetric encryption and the hashing functions. Okay. Now it is time to see the public key cryptography. This purpose, I want to remind that in the general model we have introduced we considered the fact that while defining the encryption between Alice and Bob, we said that the encryption can be symmetric or even asymmetric. We have considered for confidentiality the symmetric type of cryptography. But I want to say that the public key cryptography is the most important type of cryptography for the asymmetric case. So today, when we say asymmetric, we generally mean public key cryptography. But they are not exactly the same thing, because public key cryptography is a type of asymmetric cryptography. But maybe there are other types of asymmetric cryptography, just we don't know now about other types. So for now, the most important type, the unique type of asymmetric cryptography is public key cryptography. So if we remind the general model again, the asymmetric cryptography can be considered by having Alice that is sending a message to Bob, Alice is doing an encryption of the message. This is the plain text. Also, Alice is using a key. Let me call it KA. And then we obtain the ciphertext. And on the side of Bob is receiving the ciphertext, and by using a key, Bob will get back the plain text. In the general model, we consider the case where KA is equal to KB. This is the symmetric case. Meaning that Alice and Bob should be sharing a secret key that only Alice and Bob are knowing. But it is interesting the case where KA is different from KB. Oops. I'm sorry. This is the asymmetric case. Now I told you that the most important example of asymmetric cryptography is the so-called public key cryptography. Let me explain the meaning. So imagine that every user is having not one key, but is having a pair of keys. So Alice is having a pair of keys. This is one key, and this is the other key. And Bob is having also a pair of keys. Everybody is having a pair of keys in this world. And what is important to say is that when we are considering the symmetric cryptography, the symmetric case, if we have, for instance, I don't know, five spies that are in another territory, and the five spies should communicate using symmetric cryptography, they should be using a different key for every partner of communication. So we have a key for this one, another key here, another key, and so on. Okay. In general, for letting many people communicate in a secret way, n people, then we need n times n minus 1 divided by 2 different keys shared between all possible pairs of persons. Indeed, this number is the number of possible pairs of persons by considering n persons. So it is a quadratic number of keys. This means that there is a big number of keys, and every person should handle n minus one different keys. And this is not really simple. And it is important to compare this fact with the case of the public key cryptography, where every person is just handling a pair of keys. And while adding new persons, so the number of persons is growing, the number of keys is linearly growing. I mean that just the new persons, they will have the pair of keys, but the old pair of keys for the old persons, they should remain the same number. So this approach is letting people manage a smaller number of keys. So what we should remember is that every single user is having a unique pair of keys. Okay, this should be important. Every person should be the owner of a single pair of keys. It is still true that the key is the usual sequence of bits, and it is not having any probability different from 1/2, meaning that whatever sequence of bits, they should be having the same probability. And the single person is having a pair of keys, but the pair of keys is related. I mean that this key is related to this other key. This is meaning that every single person, like Alice in this case, is having a pair of key that is related by some mathematical properties. For reminding the relationship, I draw this arrow here. Okay, now I will be explaining better the relationship and the meaning of this fact. Okay, let's focus on one single person, one user. Because I told that every user is having a pair of keys. So this is the pair of keys. This is one key, and this is the other key. And the use of parentheses here is a typical approach of the mathematicians that are describing a pair of numbers. In our case, is a pair of keys, by enclosing them in parentheses. Okay, and what is important is that the two keys, they are having a special name. One key is called the public key. The other key is called the private key. The first meaning is that public and private, they are used because the public key is known by everybody. This is really public, not secret. You can print the public key in your web page. But remember that every user is having a public key. And associated with the public key, there is the private key. And the meaning is that the private key should be kept secret. Nobody should know the private key, okay? Only the single owner should be having the knowledge of the private key. And every person is having a private key, of course, and in addition, a public key. But every key, it will be generally different. This is just one part of the explanation. There is another part that is more, it is very important. But I want to ensure that this first part is clear enough. Any question about these points? Is it clear that every user is owner of a pair that is a private and a public key?
Yes.
The public key, by definition, is public, so it can be communicated to everybody. In addition, I will do whatever for communicating my public key to everybody. And the private key should be kept secret, completely secret. And if it happens that my private key is known by some other person, I immediately say that the private key is compromised, and I'm losing my security. This is working good just if the public key is really public and the private key is really private. Okay, this is the first part. The second part is the relation between the two keys, because let me call the two keys A and B. Sorry, let me change the name. R and S. These are the two keys. One is private and the other is public. Which one? I don't care. So R can be both the public or the private. And S is the opposite, of course, the opposite of R. And the property, the mathematical property that is wanted is if I encrypt information T by means of R, then I can decrypt, let me use another symbol. The encryption of T is T prime. I can decrypt T prime and obtain back T by using S. So this means that I can choose whatever key between the private and the public. If I encrypt with the public key, I can decrypt by using the corresponding private key. If I encrypt by the private key, I can decrypt by using the corresponding public key. This is the mathematical relationship. Is it clear? Should I repeat? Because you see in this formula here, we can encrypt and decrypt by using R and S. And R and S are whatever keys of the pair. They can be the public or the private. And the other key, it will be the opposite, of course. If R is the public, S is the private. If R is the private, S is the public. Is it clear? This is very important. Because now we understand some other properties, because in particular, we start understanding that encryption is not necessarily meaning confidentiality. It can be different from confidentiality. Because if we use this type of encryption, we don't get confidentiality. Let's check it. So we take Alice. If Alice is encrypting a plain text by using the private key, only Alice can use the private key of Alice, because the private key of Alice is owned by Alice, and nobody other can know this private key. It is secret. Okay, we encrypt the plain text, and we get the ciphertext, of course. If we look at the ciphertext, we carefully examine the ciphertext, what we are viewing. We are viewing a strange sequence of 0 and 1s, and we don't understand anything. This is the usual situation when we are examining the ciphertext. The ciphertext is never meaning anything useful, right? But let's consider this other box, doing the decryption. Since I am encrypting by using the private key of Alice, what key should be used for decryption? There is a unique key that is good for decryption. And this is the public key of Alice, right? Because I am encrypting by using a private key, so I will be needing the public key, the corresponding public key for decrypting, and I will get back the plain text. Now the question is, who can do that? If we look at the Alice side, we understand that only Alice can do that, because the encryption is made by using the private key of Alice, and only Alice can can use the private key of Alice. The decryption is needing the public key of Alice. This is meaning that everybody can access, can find the public key of Alice and use the public key for getting the plain text from the ciphertext. So it is still true that the ciphertext is meaning nothing. It is just a sequence of bits. And we understand nothing by seeing the ciphertext. But every user, every person will be able to use the public key of Alice for decrypting the ciphertext and for finding back the plain text. So it is meaning that this is still encryption, but this type of encryption is not providing any confidentiality because everybody can decrypt. Right? Are you okay? This is very important because this is the base of a big part of cryptography. This is the base for doing also the authentication. I don't know if you have a smartphone and you unblock the smartphone by using the fingerprint or by using the face. This is the logic that is used for unblocking the smartphone. Public key cryptography. We need to understand how, but then we will be more precise. For now, it is important that we understand these two properties. The first property, it is very syntactical. This is a public key and a private key, and everybody is having a pair of keys. And with each key is corresponding another key. And this is a mathematical relationship because it is not true that if you encrypt by using one key, you can decrypt by using the other key. So the two keys should be mathematically related. And this was a very tough problem because this model was introduced by a couple of guys. The general model, oops, of public key cryptography was introduced by two guys, Diffie and Hellman. They were genius because they could imagine a lot of things. The only limit was the fact that they stated the properties of the keys and they were not able to find a mathematical solution. So just they claimed, they stated the properties of the keys by saying one is public, the other is private. We will be using the public in this way, the private in this way. I will tell you. But what is important, they were not able to find a solution to define exactly under a mathematical point of view how these keys could be obtained. If I'm not wrong, this was like in the 75. 1 year later, 3 other researchers genius again. They were Rivest, Shamir, Alderman. They solved the problem stated by Diffie-Hellman. They were able to find the mathematical property. They were able to write the mathematical property that defined the private, the public key, and let the people generate a pair of public-private key. Okay? Look, there is an important property, but it is not structural. Just look at this fact. These keys are long keys. I mean, the symmetric keys, they were 128 bits or 256 bits. In this case, we have much longer keys, and the typical length of these keys is 2048 bits, or even 4096. And until some years ago, people were using this length, 1024, but now it is not longer secure. Okay, so while time passes, we need the longer keys. This is always true. But the keys we use in the public cryptography, they are longer than the keys we use in the symmetric cryptography. And this happens for several reasons. We will see some reasons, but it is not simple. Okay. Any question? Let me go back to this picture here. Let me use another color. Imagine that Alice is doing again the operation of sending a plain text to Bob and encrypting this plain text. But this second time, Alice, this is the second time, again the plain text. But the second time, Alice is using the public key for encrypting. Which one of Bob? Again, we obtain a ciphertext. And again, Bob wants to decrypt, and for getting back the plain text, Bob will be using the private key of Bob. Question: who can do that? Everybody can do what Alice is doing. Everybody. Because everybody can know the public key of Bob. So for doing this operation of encryption, everybody can do the encryption because it is only needed the public key of Bob. And then the result of this operation is it will be a ciphertext again. Very good. But notice that this time when the ciphertext is received by Bob, only Bob can do the decryption, because the private key of Bob is needed, and only Bob is knowing the private key of Bob. So you understand that in this case, we get another result, because in this case, the ciphertext is implementing the confidentiality, because only Bob can decrypt. Okay? So if we encrypt by a private key, we don't get confidentiality. If we encrypt by public key of Bob, we get confidentiality, because only Bob can do the decryption. But notice, please, that for doing that, Alice is not communicating to Bob any other information, because Alice is assuming that Bob is able to use the private key. So if we know that everybody is having a pair of keys, we can send the ciphertext and we can get the confidentiality without the need of sharing a key. In the symmetric encryption, instead, we need to share a key. So we see that while using a public key encryption, we can get a first type of ciphertext that is not implementing confidentiality. The second type of encryption is implementing confidentiality, because only Bob can decrypt. But what is important is the fact that no key should be shared, like in the symmetric key approach. And remember that in the symmetric key approach, sharing a key is an issue, a problem to be solved. How to share a key? And it is not simple, because if the adversary manages to know the key, the adversary, it will be able to decrypt the ciphertext, breaking the confidentiality. Any question? Okay. And I assume that all of you have understood the meaning of encrypting by one key, private or public, and decrypting by using the other key. I told you that Rivest, Shamir, Adelman, later, they were able to produce a pair of key having these properties. And their approach, let me go back to blue. Their approach, oops, no. Is this blue? Okay. Is known as an algorithm called RSA. This is a very important algorithm, and it was provided in the 70s, more than 50 years ago, and still today RSA is a very important algorithm, and it is having high importance. It is very popular, it is very elegant, and it is really used. Okay? And for understanding the details of these algorithms, it is needed some mathematical description, but I don't want to go deep in mathematics. So I will give you some rules without explaining the reason why these rules are good. And you should be learning by memory these rules and to be used then to use the rule, and they are not so many, so it is somewhat simple to remember some details about this type of encryption. So what I'm meaning is that the approach called RSA is the first public key cryptographic algorithm provided by humans. But today, it is true that we have many other public key approaches, but no approach is as clean, as neat like RSA is. So it is still worthy to study RSA and to take it as a very good example. Do you know that the most important prize for computer scientists? It is not the Nobel Prize, because when the Nobel Prize were instituted, computer science was not existing yet. Later, they invented the computer science. So the most important prize for a computer scientist is the Turing Award. This is an international prize. It is the most important premium. So it means that it is like a Nobel. Why I am saying this? I am saying this because the three researchers, Rivest, Shamir, Adelman, they got the Turing Award for RSA and for the importance of RSA in whatever. Today, the internet, all of you are using the internet in a very traditional way, and you also do e-commerce, and you buy items, things by using your computer. And for doing that, you use a secure transaction system. You use the credit card, and you know that the operation is secure. All of this is made secure by using RSA. So this is very important and very commonly used. Until 2000, it was patented. Then later, it was free. So today is free to use the RSA. So while patented people, they were not really using, but later all people, they started to use the approach. So let me spend some words describing how the RSA approach is working. Do you have any question? Okay. So the whole story begins when we say that we consider two numbers, P and Q. They are primes. Prime numbers. They are very large. Okay? And we call it big N, the product, P times Q. And we rely on the fact that the product of two large prime numbers is very, very big. And if we analyze the number N, and we ask to know the primes P and Q that are defining N by means of the product, the problem of factorizing N factorization is very, very, very hard. For modern computers, this problem is very, very hard, especially when the number N is having thousands of digits. Very, very hard means that the computer can work for like 1,000 of years. So it means that in practice, it is impossible. Nobody can use the result. Okay? This is the beginning of the approach. So imagine you are Alice and you want to generate the pair of keys, the public and the private key. And you start by creating, by generating a pair of prime numbers, P and Q, and you compute the product of the two numbers. Okay, this is Alice. So Alice is knowing P, is knowing Q, and can compute the result of the product. Notice that the product is easy. The inverse of product, the factorization, is hard. Like to say, if we compute the product, we cannot go back. Is it clear? It is important.
It's clear.
Very good. Now, there is a number, a special number. Why is this not blue? Okay. This is not of the color I want. Okay, it is not important. There is a special number this is a definition. It is called the totient number. More precisely, the totient function. It was invented by Euler. And this number is defined as the max let me write better. It is denoted by phi. By definition, phi of a number n is the max number. No need to say the max, the number of integers that are smaller than n, and they are having as greatest common divisor between, let me call this number m. The greatest common divisor between m and n equal to 1. This is meaning coprime. So the totient function of a number, whatever is this number, is the number of integers that are coprime with n. This is just a definition. Typically, if we want to compute the totient function of m, and m is prime, this is n minus 1. What is interesting, if we compute the totient function of a product like P times Q, we call it this product N. This is P minus 1 times Q minus 1. And this is denoted by phi of n. So just remember that this we have this special number called the totient function. That is getting from a starting number a new number that is having a particular meaning based on prime numbers, greatest common divisor, and so on. But we are not using the meaning of this totient function. Just it is important to remember that given n, it is defined phi of n, and notice please that is n is given and it is public. Phi of n is not public because for computing phi of n, it is necessary to know p and q. And for knowing p and q, it is necessary to solve the problem of factorization. That is a very hard problem. So typically, if I give you n, you cannot find phi of n. I mean, it is easy for small numbers, but for very, very big numbers, it is very hard to find phi of n. So given n, phi of n is a secret. Only Alice that is generating all things is able to know phi of n. Otherwise, other people cannot compute phi of n. Okay? So remember, n is the product of two large prime numbers that are chosen by Alice in a secret way. And after choosing P and Q, Alice can compute the product of P and Q, that is n. And n is a number that can be made public also, because by knowing n, it is impossible, almost impossible, to get phi of n and to get also p or q. Okay? So don't give a particular meaning to phi of n, because the meaning of phi of n is important only for proving the theorem, but we are not proving the theorem that is making RSA completely working. We are just giving the rules, and we don't want to go into mathematical details because too hard. Not so hard, but maybe too hard for young students. So this is the beginning. How to continue? Remember, we are describing the operations of Alice. So first operation is creating P and Q that are large primes. After creating P and Q, Alice can compute the product n, that is P times Q. Also, I told you that it is defined this function phi of n. This is known for Alice. Unknown to others. And we know that phi of n is p minus 1 times q minus 1. Notice, please, that since p and q are odd numbers, they are prime, so they are odd. It means that p minus 1 is even, and also q minus 1 is even. So phi of n is an even number. Now, Alice should be creating, should be choosing a number called E, such that I am saying that Alice should be choosing a number E, should be arbitrarily choosing a number E, such that E is between 1 and phi of n. And the greatest common divisor between E and the phi of n is equal to 1. So they are coprime. These numbers, they are coprime. No divisor, no common divisor. Okay? Now, how to continue? So Alice is 1 generating P and Q. 2, choosing a number E so that E is not exceeding a phi of n, and it is also coprime with the phi of n. Coprime means that the greatest common divisor between E and phi is 1. Now, we compute step number 3. We compute Alice compute. A number D such that D times E is equal to 1 mod phi. I think that you have already met the modular operation, right? Do you know the meaning of mod phi?
Yeah.
Okay. People loves to say, they love to say that D is the multiplicative inverse of E. Another point that is equivalent E is the multiplicative inverse of D. Okay, so mathematicians like to write that D is equal to E raised to the power of -1, and that E is equal to D raised to the power of -1 mod phi of n. What is important is that the product between E and D is equal to 1 mod phi of n. Okay, so let's remind step number 3. says, Alice, you should compute a number that is the multiplicative inverse of E, mod phi of n. And so Alice should compute this number. Now, the public key is a pair En. The private key is a pair Dn. So if we link back this new information, how to generate the keys to the old information, that is meaning the private key, the public key, Alice is generating the prime numbers, it is computing, is choosing number E, and all this information is providing a public key. The public key you see is just the pair E, big N, and this is a public, completely respecting the definition of public key. So we can make it public because people will find very hard, very, very hard to get the P and Q from N. And the private key is basically this number. By definition, is the pair Dn, but the very secret part is D, because it is the multiplicative inverse of V. Notice, please, that E is public by definition. The multiplicative inverse of E is not public. And this multiplicative inverse is the inverse mod phi of n. And phi of n is not public. So it is hard to find the multiplicative. Oops, sorry, I pushed the wrong button. Can you see? No. Let me find the. Okay. What I was meaning is that given E, it is very hard to find D. And also given D, it is very hard to find the E, unless you know all information. I mean, if you are Alice, from D you can compute E, because you know phi of n, that is the tangent function. Okay, this is the way to generate the public key and the private key. So we have seen how to generate the generation of public and private key. it's a little bit tricky. Are you okay? Should I repeat anything? Are you with me? I don't hear anyone.
Yeah, it's clear. At least to me.
Okay. So I hope it is clear enough. And this is the rule how we can generate the keys. Now, how to do the encryption? So we have seen how to generate the key. How to encrypt? Now we are assuming that we are encrypting a number. Oops. We are encrypting a number M. Okay. And the encryption of M is given by another number that is called C, like ciphertext, that is M to the E mod N. And the decryption of C is M equal to C to the D mod M. Notice, please, that the encryption and decryption operations, they are quite symmetrical, and you can exchange. This means that this encryption is encrypting by using the public key. This is public. But you can use this approach in the other way, and you can encrypt by computing C is equal to the M raised to the power of D mod N. If you do that, then your original number, it will be C to the power of E mod N. Okay, so you use the same function for encryption and decrypting. You can encrypt and decrypt by using the power, just is changing the exponent. Okay, any question? Okay, this is very important. And if we have time enough, I am not sure that we will be having time enough. I will show you a fast algorithm for computing the power, because these numbers are very big number. And for mathematical soundness, we need that M is, oops, typically M is smaller than N. If we want to encrypt a bigger number, we need some operation modes, but typically they are not used for that. So we are just assuming that we want to encrypt a number. The question is how to encrypt a text. This is the same. If we, oh, again, sorry. Sorry, it's my fault. I was saying how to encrypt a text. You know that if you have a text, the text is a sequence of bits, right? And the text can be interpreted as a number. It is right. It is really immediate to interpret a text as a number. So if we say that we are encrypting a number, we are general enough because whatever text can be interpreted as a number. Just if the text is too long, it can happen that the number is too big. But notice, please, that we need that the number should be less than n, but n is very, very big. So a very, very long text will give a number that is greater than n. And in that case, we will be needing to decompose the text in many blocks that are smaller than n. And we will be needing to use a operation, a mode of operation, like in the symmetric ciphers. But we are not really using that because since the encryption is the exponentiation, it is a very general heavy operation. We prefer to encrypt only small information. And in particular, if we are using devices based on battery, we don't want to drain the battery. And we don't want the devices computing all the time big numbers. And we will be trying to use small numbers. And this is what it really happens. So I hope this part is clear enough, but there is another important part. Any question? Okay. Let's step forward. And the next speech is related to the fact that if we are encrypting by the private key, is this useful? Because we have seen that if we encrypt by means of a private key, everybody can decrypt. because everybody can use the public key, the corresponding public key for decrypting the ciphertext. So we don't get confidentiality. So if people are able to decrypt by using the public key, people will understand the one important things. If you can decrypt by using the public key of Alice, what do you understand? That only Alice could encrypt because it was encrypted by using the private key. Okay? Let me repeat. If you decrypt a ciphertext by using a public key, you don't have any confidentiality. But all people that will be decrypting by using the public key, they will understand that only Alice could be encrypting that information, producing the ciphertext, because only Alice is the owner of the private key, of the corresponding private key. So still the association between the public key and the private key that is very important. But this is generating a method for ensuring that you can understand who is to generate that ciphertext. Only one person could be generating the ciphertext. It is not confidential, but it is giving information about the only person who was able to generate that ciphertext. Do you understand?
Yes.
This is critical because it is a fact that the encryption by private key is providing no confidentiality, but it is providing non-repudiation. So this is today accepted in most part of the world. If you are encrypting by means of your private key, you get no repudiation. You cannot say it was not me doing the encryption. And this is leading to the concept of digital signature. Okay, non-repudiation means that we are. Do you remember when we started? We introduced the requirements of information security, and one of the requirements, the possible requirement, it was the non-repudiation. You cannot say it not me, because there is something that is denoting myself, and I cannot repudiate this because the whole system is constructed so that I cannot share my private key. If I share my private key, it is true that other people can use it, but the key is compromised. So the non-repudiation is lost. Okay? So unless the private key is compromised, you have the non-repudiation. And this is generating the the idea for obtaining the digital signature. Any question? Okay. Remind that it is very important to be able to use a public key, because the public key is public. Okay. What if the attacker is providing to you a fake public key? You don't know. The public key is looking like a sequence of bits. You cannot understand if the public key is correct or incorrect. So the attacker can be providing a public key by saying, this is the public key of Alice. But really, that is the public key of the attacker. How can you understand the difference? Can you? The problem is that you cannot. Nobody can understand the difference. So it is easy to cheat about this fact by providing fake public keys, and we need to be sure about the ownership of a public key. Do you understand the idea, the concept? It is very important to be able to associate a public key to a single user, because if you associate the public key to the wrong user, you lose the non-repudiation. If you want the non-repudiation, you need to be able to associate the public key with the correct owner. So there are three elements. The public key should be associated with the private key, and should be also associated to the owner. The first association is just technical, because you need it working, and you need that properties that we saw. But the second association between public key and the owner of the public key is important to prevent cheating, and you want non-repudiation. So you need a system for ensuring the ability to associate a public key to every person, to a single person. But you can ask, why not associating a private key to a single person? While it is true that the private key is associated with a single person, this is true, no doubt. You cannot state this, because you cannot describe the private key, because the private key is a secret. So you cannot talk about the private key. So you can talk about the public key, and you can associate the public key with a person. And there is a private key associated with the public key. Is it clear? So what it should be clear is that you need to associate a public key with a single user without errors. Is this clear?
Yes.
Very good. And now I want to describe the mechanism for associating a public key to users. Keep in mind that when I say users, a user can be a person, can be a software, can be an internet domain, for instance, if you say google.com, this is an internet domain. And a public key has been associated. Then I will teach to you how to find the public key. What is important to say is that very often you can have a public key. Let me call this key K. This key is the key of the domain. It can be associated with the domain or also can be associated with the owner of the domain. Do you understand the difference? It is very similar. You can associate a public key with the domain or with the owner of the domain. In the first case, you associate the key with a thing. In the second case, you associate the key with a person, with an organization. Keep in mind this difference because it is producing some effect. Also, associating a public key with software is not the association with a person. It is associated with a software, but you can associate the public key with the producer of the software, that is a person or it is an organization. Same difference. Or directly you can associate the public key with a person. Okay? Now, how to associate? There is a mechanism called the mechanism of digital certificates. Typically, when you are talking about digital certificates, you just say certificate. So the word digital is not really used. So they are digital certificates, but people just use certificates. And the standard that is saying how to do this association is called X509. Today we have a version 3. So it is very typical that people will say, what is your X509 certificate? And this is an international standard, and all the world is using this standard. And it is a standard that is letting the internet working. Otherwise, the internet could not be working. And you can imagine this digital certificate like a document, a digital document. This is the digital certificate. Containing several information, but the most important part of this information is a name and a public key. So the result is associating the public key so the public key is associated with the name. Okay, so we have certificates associating public keys with the names, and name is very general. Software can have a name. Internet domains can have a name. Person, they have a name. So by using a name, you can describe whatever, and the public key is associated with a name. So this means that if you want to describe your public key to another person, I want to give you my public key. A way that I can use is I give to you the digital certificate containing my association Fabrizio D'Amore, that is the name, with my public key. Okay? So a way for distributing is giving a certificate. Remember, a certificate is a digital document. It appears as a file, of course. And it is containing a public key. What is important? Digital certificates are emitted by certificate authorities. People used to refer to certificate to a certificate authority by using CA. So what we are understanding is that a certificate authority is producing a digital certificate, and this digital certificate is associating a public key with a name. Okay? And typically, CA CAs, they should be trusted. Trusting is not an automatic operation. You need to say to your device, trust these certification authorities. There are many certification authorities, and maybe you want to trust some of them. You can choose what certification authorities you want to trust. All your devices are already trusting some certification authorities, and maybe you don't even know that they are trusting these certification authorities. But when you buy a new device, it is already trusting some certification authorities. You can change if you want. You can untrust all of them, and you can choose which one you want to trust. But normally, whatever device is already trusting a certification authority. The trust is meaning that it is a choice of the user. You can trust. But if you don't trust, you don't believe the certificate. So all certificates, they are written according to the standard X5 of 9, version 3. But if I have a very old certificate that is version 2 or version 1, this can be still valid. This can be still valid because the version 3 is having the backward compatibility, including the old versions of the standard. But the modern version is this one. Okay? So this document is having this information. Very typically is having another couple of information that is a start date and a stop date. So it means that the certificate generally certificates are valid within a time interval. So while the certificate is valid, you can use it. But if you try to use a not valid certificate, you will meet an error, and whatever device in the internet will stop talking to you because you are not showing a valid certificate. So it means that you can be a fake. But the real reason why digital certificates are expiring is that you have to pay for getting a certificate today. The business model is that the certification authorities, they are asking to be paid for emitting digital certificate. So digital certificates are expiring because certification authorities want to be paid again later. So maybe you get a certificate that is valid for 1 year or 2 years, but normally they are expiring after a few years. And if you want, you can get a digital certificate for just 1 month, but maybe it is not really interesting. Keep in mind that the longer is the validity of the certificate, the more you will be paying for getting it. Of course, this is just a business observation. And not only certificates are expiring. There is another problem. Certificates can be revoked. Because if I have a public key and I have a certificate, then imagine it happens that my private key is compromised. If my private key is compromised, the certification authority that has provided to me the certificate, the certification authorities should be saying, okay, your certificate is revoked because your private key is compromised. Another reason why certificates are revoked is the following. You must know that my school, my university, let me have a private key because I am a university professor and I use the private key while I am a university professor. And just for that, if tomorrow I will be retiring, for instance, then I cannot any longer use my private key. What is the mechanism for preventing me tomorrow by using the private key? The mechanism is the same, revocating the certificate. So if you have a certificate that is valid from the starting date, until some ending date, and for whatever reason I wanted to revoke the certificate this time, the problem is that this time key is not written in the certificate because the certificate is showing the time T1 and the time T2 for starting and ending. So if I want to revoke this certificate, I need to find a mechanism for informing people that the certificate has been revoked. Is it clear? For this reason, certification authorities are emitting CRL, that is a certificate revocation list. Another information that is containing the certificate here is the serial number. Every certificate is having a different serial number. And here, the CRL is just a list where, the CRL is a list where is again a digital document. According to the standard. and it is containing some information, a lot of information, but in particular, the most important part is a serial number, revocation date, another serial number, another revocation date, and so on. A long list. I don't know the length. It is long, this list. And typically, certification authorities are producing this list of revoked certificates every 2 weeks. Let me write every 1-2 weeks. Okay, so when you are getting a certificate, you should be analyzing the correct CRL for checking whether the certificate has been revoked or not. Because in many cases, attackers, they manage to use a revoked certificate for deceiving you and letting you believe something that is not true, for spreading fake information. And for giving more details about that, we need to spend a few words, some few more words about this check, about revocation, and about the use of digital certificates. But this is a long discussion that today we cannot do because the time now is expired. So in the last 2 minutes, I ask you if you have any question about this subject. And keep in mind that the next time we will be continuing the description of asymmetric cryptography until reaching the definition of digital signature, because it is that type of information that we are trying to achieve. So, any question from you? Is this all clear?
Yes.
Yes.
So I want to just suggest, let me share another how to share it. So where is it? Let me share this. Do you see my screen, my new screen?
Yes.
Yes. This is a browser. And when you go somewhere like Google, you see the page, right? And here you can find some information about the website. And here you can inspect the certificate. So I recommend you to check your browser for looking at the certificate and for trying to get some information from the certificate. After this operation, you will have several questions. I imagine you will want to ask some questions, and the next time I will be answering your questions. But please check your certificate in your browser. This is the certificate for Google, but whatever website you are visiting, if the website is, for instance, let me close this, is Facebook, you can inspect again the digital certificate. You see that also this certificate is good from January to April, and they will be soon renewing the certificate. But you can analyze all details of this certificate. You see that the version is version 3. This is the serial number. This is the certification authority. Starting date, ending date, other information. So I want you to be familiar with this information because they are very important. They are on the base on the functioning of the web and the internet. So if you don't have any question, I thank you for your attention, and I just wait a minute. Let me go to Meet again. Okay, okay. And we meet again in 2 weeks. Thank you again, and goodbye. Have a good day.
No, we thank you.
Goodbye.
Have a
Have a good day.
buona notte.